So we're going to do a lesson on linear approximation. This is just sort of a review of some of the ideas we've already covered in D3 because all we're doing is finding slopes of tangent lines. Okay, so let's look at a graph of what we're going to do. I have my function f of x here. I'm interested in writing the slope of the tangent line to this function at some a value. Once I get that a value, I'm going to find a nearby point, and I'm going to use my red function to approximate the value of the orange function and figure out if that approximation is an overestimate or an underestimate. So here's my function f of x. I'm interested in finding the slope of the tangent to my curve at x equals a. So I would take the slope, which is represented by the derivative at x equals a. And then I would write my line. My point is a, f of a, y minus my y coordinate of my point equals my slope, which is f prime of a, times x minus the x coordinate of my point. So it's literally just the tangent line. I'm going to call y L of x to stand for linear approximation, and I'm going to move my f of a term to the right-hand side. So f of a plus f prime of a times x minus a. So every example we do, we're just writing the slope of the tangent line to the curve at the given point they want. Now let's say I said to approximate f of b, and let's say this was a point b. My approximation, L of b, is the one up here in red, is going to be bigger than my function value at b because the tangent line sits above my original function f of x. So here, this approximation will be an over approximation. If the tangent line sat below my function, then the approximation would be an under approximation for my original function. So this would be an over approximation because the tangent line sits above my function. Okay, so let's look at the first example. I want to find the linear approximation. This is just the slope of the tangent line to the curve at the given point. A is 0 in this case. So f of 0 plus f prime of 0, x minus 0. So f of 0 is just sine of 0, which is 0, plus f prime of 0. Well, my derivative at my function is cosine x. F prime of 0 is cosine 0, which is 1, times x minus 0. So in this example, my linear approximation is just x. That's the equation I'm using to approximate any tangent or any y coordinate on my original function. So I could ask you to do L of a value close to 0. So let's say we take 0.2. L of 0.2 would be 0.2 because I'm subbing it into x. My function value at 0.2 would be equal to sine of 0.2. Make sure your calculator is in radian mode. 1.98669 dot dot dot. And you can see that my approximation is over approximated. And this is because the tangent line sits above the original function at this time. If I took a value that's a little bit further away from 0, which is 1, and I say, what is my function value at 1? Well, sine of 1 is equal to 0.841. So again, my approximation is a little bit further than my actual value. It's still an over approximation, but again, the closer that my the closer my point is to this a value, the closer the approximation will be to the actual value. Okay. Find the linear approximation of the function cosine x at L or at a equals pi over 2. So I'm going to do my linearization, my linear approximation. My slope of the tangent line to this curve at this point is f of pi over 2 plus f prime of pi over 2 x minus pi over 2. So f of pi over 2 would be cos pi over 2, which is 0. F prime of x, the derivative of cosine is negative sine x. The derivative at pi over 2 would be negative sine pi over 2, which is negative 1. So minus 1 x minus pi over 2. And then my cleaned up version is minus x plus pi over 2. So I would use that to approximate any value of x on the original function by using this. And again, the further I am away from pi over 2, the further my approximation will be. It will be less accurate, but it's still an approximation nonetheless. Okay, linear approximation of a function at an a value. Linear approximation is f of 1 plus f prime of 1 x minus 1. So f of 1 is 2 times 1 cubed minus 3 times 1. It's negative 1 plus f prime of 1. Well, let's do f prime of x first. 6x squared minus 3. F prime of 1 would be 6, 1 squared minus 3, which is 3. So 3 times x minus 1. Clean it up a little bit. 3x minus 3 minus 1 is minus 4. And there's my approximation, my linear approximation. I would use that to approximate whatever value of the function I wanted. I could approximate f of 1.1. I would use this, sub in L of 1.1, and then I could approximate it and figure out, is it an over, is it an under, example like that. Find the linear approximation of the function, L of x equals my f of 8 plus f prime of 8, x minus 8. So square root 1 plus 8, square root of 9, which is 3. I take the derivative, which is chain rule. So I bring down the 1/2. I get 1 plus x to the minus 1/2, so I'm automatically going to write it on the bottom as 1 plus x. And then the derivative of the inside of 1 plus x is just 1. I sub in 8 into my derivative function. And I get 1 over square root of 9 is 3. 3 times 2 is 6. And there's my approximation that I'm able to use to do anything with. So what values of the linear approximation is my linear approximation accurate to within 0.5? So I want the actual value of an approximation to be within 0.5 units of the real answer. So what we do is we say, okay, I want it to be centered around 0.5. So it has to be between, if I take the function value or the function minus the approximated function, so minus my linear approximation, this needs to be within 0.5 units apart. So if I subtract the actual value from the approximated value, this needs to be 0.5 apart. And I want to solve for the x that actually does this for me. So to do that, I'm going to add 7 over 4 on both sides. Okay, so when I do that, negative 0.5 plus 7 over 4 is 1.25. So 1.25 has to be smaller than root x plus 3 minus x over 4, which has to be less than 2.25. Okay. Now, when I do that, now this would require me to use a graphing calculator. So I'm going to sub in y is 1.25. y2 is square root x plus 3 minus x over 4. I solve for the intersections. So when I do that, I get two intersections here using Desmos. I get negative 2.657 and I get positive 8.657. And I would also want to solve y1 is equal to 2.25 and y2 is equal to square root x plus 3 minus x over 4. And in this case, I get no intersection. So when I actually solve this, I get kind of a range here. So my x value would have to be between minus 2.657 and 8.657 for me to be able to get my answer within 0.5 of the real thing. So I would want to try to choose x values as close in this range as I could to make sure I am within 0.5 away. Now you can do, as you're practicing, you can do it within 0.1. We would just change those two numbers to 0.1. So really, when we're looking at this idea, we're taking the difference between the function and the approximation, and we want it to be within whatever accuracy we want. And then again, you use that process to solve. And that's the lesson.